I mean, I want you to imagine something for just a second.
All
Think
right.
about the kind of raw computational horsepower required to design, like, next generation materials.
Oh, right. It's massive.
Yeah, we're talking about discovering room temperature superconductors or engineering highly efficient solid state batteries, simulating revolutionary polymers, that sort of thing.
Yeah, the really heavy duty stuff.
Exactly. Usually when you picture that kind of work, you picture this massive, artificially cooled, just massively power-hungry server farm humming away in a warehouse, right?
Right. Millions of dollars of hardware.
But what if that supercomputer wasn't in a server farm at all? What if the hardware required to map out the entire future of materials science was actually, sitting right there in your pocket?
I mean, it definitely sounds like science fiction at first
It
glance.
really does.
Because we're so conditioned to think that advanced AI and these complex physics simulations, they require centralized, cloud-based behemoths. But the reality is, we're standing on the edge of a paradigm shift that decentralizes that power completely.
And that is exactly our mission for today's deep dive.
Wow.
We are unpacking a literal stack of cutting-edge research papers that provide a roadmap for, well, rendering those massive data centers completely obsolete.
Which is just a wild concept.
It is. We're going to figure out how we can run automated LAMMP MPS code generation. And for those who don't know, that's like the absolute gold standard for material science simulation.
Well, absolutely.
And doing all of that entirely on a smartphone.
Yeah, a standard smartphone.
Which is crazy. But to do this, we essentially have to solve three massive bottlenecks that currently trap AI in the cloud. We have to shrink the brain, we have to teach it to think without speaking, and we have to figure out how it can learn from its own mistakes on a tiny battery.
That's actually a really great way to frame it. Because before a smartphone can even attempt to run a physics simulation, we hit a wall with the hardware.
Right.
You can't just take a massive language model and cram it onto a mobile chip. It'll just melt the phone.
Yeah, the battery would be dead in 2 seconds.
Exactly. So the architecture has to be fundamentally rethought, which brings us to the core engine of this whole setup. It's a model called Gemma 4.
Right, and the papers specify this is a 26 billion parameter model. Now, 26 billion sounds pretty massive for a phone.
It does, yeah.
But this is where the specific architecture comes into play, right? The mixture of experts model.
Yes, the MOE architecture.
Because if I'm understanding this correctly, a mixture of experts isn't lighting up all 26 billion parameters at once. It's more like like a giant corporate office.
Oh, I like that analogy.
Right, like you have 26 billion employees, but if the task is an accounting problem, you don't wake up the marketing team and the janitorial staff. You just route the problem directly to the accounting department.
That's a brilliant way to visualize the routing mechanism, actually. Out of those 26 billion total parameters, Gemma 4 only activates about 3.8 billion parameters during inference.
Wow, just 3.8.
Yeah. The network uses a specialized router to look at the incoming problem and dynamically select only the specific expert subnetworks needed to solve it.
That makes so much sense.
Right. So this means the computational load and consequently, the power draw on the battery is kept incredibly low while the total surface area of knowledge remains vast.
So it's only using a tiny fraction of its brain at any given time, but it's the exact right fraction.
Exactly.
And apparently, this highly focused approach just punches way above its weight class. Like one of our sources, an independent AI tester, they ran this exact 3.8 billion active parameter model through a really complex causal reasoning test.
Oh, the maze test.
Yeah, the maze. It was a logic puzzle where the AI had to navigate a maze using exactly 9 button presses plus an emergency exit while adhering to strict resource constraints.
And the results from that were incredibly revealing.
Yeah.
Because the Gemma 4 model didn't just pass the test, it actually outperformed GPT 5.4.
Wait, really? It beat GPT 5.4.
It did. It beat a massive proprietary monolithic model. It showed an intense capacity for self-reflection, like it would check its own sequences, recalculate its path, and find a perfectly optimized 10-step solution where the massive models either, failed completely or took much longer, highly inefficient paths.
Okay, so we have a compact, highly optimized brain that fits on a mobile chip. That's step one. But an AI doesn't just wake up knowing material science.
No, definitely not.
Normally, training these models requires a massive data diet. You feed them millions of high-quality examples, which takes months of computing time in a server farm. So how do we bypass that for a phone?
Well, we shift from relying on data volume to relying on data precision. This is a framework the researchers call polymath learning.
Polymath learning, right?
Yeah. So instead of throwing a mountain of domain-specific data at the model, the system is trained on an extremely condensed, highly engineered meta-sample. They call it a synthetic prime.
A synthetic prime. I have to say, I love the sound of that.
It sounds very sci-fi.
It really reminds me of the movie The Matrix, when Neo is in the chair and just, like, downloads kung fu straight into his brain.
Yes.
He isn't sitting there watching millions of individual fight videos. His brain is fed one perfectly choreographed, incredibly dense sequence that teaches him the underlying physics, the balance, the kinetic energy of all martial arts simultaneously.
Let's actually build on that analogy because it highlights exactly why this works so well.
Okay.
The synthetic prime forces the model into a multidisciplinary corner. For instance, this single training sample might ask the model to calculate photon energy based on a specific wavelength, which requires physics.
Right.
Then it has to use that energy value to break specific chemical bonds, so there's your chemistry. And finally, it applies that chemical reaction to a strand sequence, bringing in biology.
But I'm still a bit hung up on this, honestly. If you only give a neural network one hyper-complex problem, doesn't it just, memorize the answer to that one problem? Like, how does it actually generalize that to write industrial-grade LAMMPS simulations it's never seen before?
It's a fair question, but it goes much deeper than just memorizing facts. What the researchers discovered is that when you force a neural network to mix disciplines like that, it has to abandon rote memorization entirely.
Really? Why?
Because the only way for the network to resolve a problem that spans physics, chemistry, and biology simultaneously is to build a highly generalized mathematical framework.
Oh, I see.
Yeah, the efficacy of this polymath sample correlates directly with the activation of advanced salient math skills, specifically things like pre-calculus and abstract algebra.
Oh, by forcing it to juggle multiple scientific domains at once, you're basically forcing it to learn the universal language beneath all of them, which is the math.
Yes, exactly. You are giving its reasoning engine an extreme targeted workout. The data shows that training on this single synthesized multi-domain sample actually yielded greater cross-domain reasoning capabilities than training on thousands of naturally occurring isolated samples.
That is just wild. Okay, so we have the Gemma 4 brain, and we fed it the synthetic prime curriculum. It understands the underlying math of the physical world.
Right.
But this brings us to our second massive bottleneck. When AIs solve complex problems, they usually, they can't think out loud.
They do, yes.
They generate a massive chain of thought, right? Just spitting out thousands of text tokens to explain their reasoning step by step before finally giving you the answer.
And if you try to do that on a smartphone, generating thousands of tokens just to plan out the architecture of a LAMMPS simulation,
Yeah.
you will exhaust the phone's memory buffer and drain the battery in minutes.
Right, it would just crash. So if it can't talk us through its process, how does our pocket supercomputer actually plan an experiment without instantly dying?
It utilizes an architecture called the hierarchical reasoning model, or HRM.
HRM.
Yeah. This is a remarkably lightweight piece of the puzzle, coming in at only 27 million parameters.
Oh, that is tiny.
It is. Its core innovation is something called latent reasoning. So instead of thinking out loud by generating explicit text tokens, the HRM thinks silently, entirely within its internal hidden states.
Okay, so standard chain of thought is like someone who has to talk out loud to solve a difficult math problem. They have to hear themselves say the numbers to keep track of them.
Exactly.
And HRM is more like the quiet genius sitting in the back of the class who just stares at the equation on the board and solves the entire Sudoku puzzle in their head.
That captures the dynamic perfectly. And to manage that internal mental load, HRM is structurally split into two distinct, biologically inspired recurrent modules.
Okay, how does that work?
Well, you have a high-level module, which is tasked with the slow, abstract planning and overall strategic direction. Then you have a low-level module, which executes the rapid, detailed, immediate computations.
So if we're designing a new battery, the high-level module is like the project manager saying, okay, we need to simulate the lithium-ion diffusion rates across an amorphous structure.
Right.
And the low-level module is the intern furiously calculating the exact atomic coordinates and boundary conditions to make that happen.
That's a great functional breakdown. And because this entire negotiation between the project manager and the intern happens in a single forward pass through the network.
Wait, single forward pass?
Yeah, without ever generating explicit text tokens, it completely eliminates the memory bloat. In their benchmarks, this tiny 27 million parameter HRM solved incredibly complex tree search logic puzzles, like optimal pathfinding in large mazes with near-perfect accuracy.
Wow.
Meanwhile, massive models that relied on traditional token-based chain of thought completely choked on the memory requirements.
So HRM gives it the ability to think in the dark, essentially. But honestly, if an AI is thinking silently in the dark, my immediate fear is hallucinations.
Oh, absolutely. That's the risk.
Like, a chatbot confidently making up a fake book title is funny. A pocket supercomputer confidently hallucinating a new law of thermodynamics blows up our virtual lab.
Yeah, that would be a disaster.
So how is it fact-checking itself without pinging a giant database in the cloud?
You're touching on the core issue of reliability in edge devices here. Normally, as you mentioned, models use something called retrieval augmented generation, or RAG.
Right.
That essentially means the AI is constantly Googling facts from a massive external database while it thinks to make sure it's accurate. But we want this to run locally, disconnected from a server farm.
Right. We can't rely on Wi-Fi to keep the laws of physics intact.
Exactly. So to replace cloud-based RAG, the system employs GraphMERT.
GraphMERT.
Yeah, this is a compact 80 million parameter encoder-only model. Its job is to act as a local neural symbolic converter.
Neural to symbolic. Let's unpack how that actually works.
Sure. So neural networks operate on probabilities, right? They are fuzzy and great at finding hidden patterns, but they are prone to guessing.
Right. The hallucination problem.
Exactly. Symbolic systems, on the other hand, like a knowledge graph, are explicit, rigid, and strictly rule-based. GraphMERT essentially acts as a bridge.
Oh, okay.
It analyzes the model's fuzzy internal representations and maps them directly onto a hard-coded map of factual scientific relationships.
Oh, I see. It's taking the AI's intuition and forcing it through a rigid filter. So the AI might think, I should bond these two atoms, and GraphMERT checks the hard-coded map and says, no, under these temperature conditions, that bond is ontologically impossible. Try again.
Yes, exactly. It guarantees that the NMPS syntax and the physical constraints being used are rooted in actual verified science.
Yep.
And it does this exceptionally well.
How well?
In tests measuring the extraction of domain-specific knowledge, this 80 million parameter GraphMERT achieved a 69.8% fact score.
And how does that stack up against a traditional massive AI? Like, what's the baseline?
A 32 billion parameter baseline model running standard processes only achieved a 40.2% fact score.
Wait, 40.2. So GraphMERT is orders of magnitude smaller, vastly faster, and significantly better at preserving scientific reality.
Precisely. It completely flips the script.
Okay, let's take a breath and look at where we are. Our smartphone has the Gemma 4 brain. It learned the underlying math from the synthetic prime.
Yes.
It can plan out a complex experiment silently using HRM, and GraphMERT ensures the physics are real.
That's the setup.
But knowing physics and actually writing a functional simulation script are two different things. Like, coding requires trial and error. So how does the phone test its LAMMPS code and fix its own bugs without a human engineer sitting there debugging it?
To solve the coding bottleneck, the system relies on a closed-loop, execution-driven optimization process. This draws heavily on the MD-Agent 2 multi-agent framework.
MD-Agent 2, got it.
Yeah, research has shown that a smaller model, like the 8 billion parameter MD Code 8B used in the MD-Agent 2 testing, can be explicitly adapted for material science without needing massive scale.
Okay, but how?
It does this by leveraging a reinforcement learning algorithm called MDGRPO.
Reinforcement learning. So we're essentially giving our tiny digital scientist a virtual sandbox to play in and rewarding it when it gets things right.
Precisely. The model generates a LAMMPS script and automatically runs it locally inside a sandboxed environment. The environment then returns an execution outcome.
Like an error code.
Exactly. It might be a basic syntax error, or it might be a thermodynamic stability check showing that the simulated material just melted. That outcome serves as the reward signal.
But if my code breaks, I have to comb through it, figure out what went wrong, and try a completely new approach. How does the AI know how to evolve its code based on a failure?
This is driven by something called the Darwin-Gödel Machine Framework, or DGM.
DGM.
Right. It's designed for open-ended evolution. The system maintains an archive of all its past coding attempts. When an execution fails in the sandbox, DGM uses parent selection.
Parent selection.
Yeah, it looks back through the archive and selects the most promising previous versions of the code, the best stepping stones, essentially.
So it's essentially using natural selection. It looks at its past attempts, finds the genetic code of the runs that survive the longest, and breeds them.
That's exactly what it's doing.
But mechanically, how is it combining them? Like, code isn't DNA.
It does it through a fascinating process called the trace and rewrite mechanism.
Trace and rewrite.
Right. When a script fails to compile, the system doesn't just delete it or start over from scratch. It reads the execution error log, traces exactly where the logic fell apart, and then splices healthy syntax from a successful older script into the broken new one to bypass the error.
No way.
Yeah, it's literally recycling its failed trajectories to continually refine its own code generation strategy.
It's performing genetic surgery on its own logic. That is incredible.
And the performance leaps are empirical. Through this open-ended trace and rewrite exploration, DGM improved benchmark coding scores, specifically on SWE bench from 20% all the way up to 50%.
Wow.
It learns to produce industrial-grade simulation scripts entirely autonomously.
But wait, this brings us to kind of the final boss here, the absolute hardest hardware problem of them all.
Right, memory.
Yeah. For the digital scientist to truly learn from those sandbox experiments and permanently improve, the neural network has to update its own weights. It has to perform backpropagation.
It does.
And doing backprop on a battery-powered device, I mean, I thought that was fundamentally impossible due to the memory constraints.
It has historically been the ultimate bottleneck. Standard backpropagation through time, or BPTT, requires the system to save a massive step-by-step history of its states.
Right.
The memory required scalars linearly with time, what we call O of T memory. If your smartphone tries to log the entire history of a multi-step thermodynamic calculation just so it can review it later, the memory buffer overflows and the device crashes.
Not to mention, standard networks have an issue where deeper layers get drowned out, right? Like, the longer the sequence goes, the louder the early steps become, and the new information just gets lost in the noise.
You're referring to pre-norm dilution.
Yes. Exactly.
Because standard residual connections just blindly add the output of one layer to the next, the mathematical magnitudes keep growing. Deeper layers have to produce massive unstable outputs just to exert any influence, which completely destabilizes the training process on a small device.
So if standard BPTT requires us to keep a massive logbook of every single step, and we don't have the memory for a logbook, we essentially have to find a way to learn the lesson without reading the history. Are they using some kind of intense data compression?
It's actually more elegant than compression. They replace standard residuals with attention residuals, or address.
Okay, attention residuals.
Instead of blindly accumulating outputs, the network applies a learned softmax attention over the previous layers.
Meaning the network gets to choose which specific past layers were actually important, and it actively ignores the rest.
Exactly. It bounds the mathematical magnitudes and distributes the learning gradients much more uniformly. But the true breakthrough, the thing that solves the memory crisis entirely, happens when attention residuals are combined with the hierarchical reasoning model's one-step gradient approximation.
One-step gradient.
Yes. By doing this, the memory footprint required to update the model drops from that massive RT down to a constant O of 1.
Hold on. I'm going to have to push back on this.
Okay, go ahead.
You're saying O of 1 memory, which implies it only needs to look at the very final step to understand everything that happened.
Yes.
But human learning doesn't work like that. Like, if I bake a cake and it tastes terrible, that's the final state, right?
Right?
I can't just look at the burnt cake and instantly know that I preheated the oven 50 degrees too hot or that I mixed the flour in the wrong order. I have to trace my steps back. How can the AI calculate a learning gradient just from the final state? Doesn't it lose the how?
That is the exact intuition that makes standard BPTT seem so necessary. Your cake analogy assumes that the process is destructive and messy.
Which my baking usually is.
Fair enough. But the internal hidden states of our HRM aren't a baked cake. They are a mathematical system. This is where the elegant mathematics of deep equilibrium models, and specifically the implicit function theorem, come into play.
Okay, you're going to have to ground the implicit function theorem for me.
Think of it less like a cake and more like a physical landscape. Imagine rolling a ball down a complex, bumpy hill. Eventually, the ball comes to rest in a valley. That resting point is a true, stable, local equilibrium.
Okay, I'm with you. The ball has settled.
Now, if you're a physicist, you don't need a video recording of the ball bouncing down the hill to understand the forces at play. Because the ball is at a perfect equilibrium, the exact angle it's resting at, the pressure it's exerting on the ground, the precise shape of that resting point, all of those metrics inherently describe the surrounding topology. The implicit function theorem proves mathematically that you can calculate the exact learning signal directly from that stable fixed point without having to unroll the sequence of steps that led to it.
Oh, wow. Because it reached a mathematical equilibrium, the final state is fundamentally bound by the parameters that created it. The resting point literally contains the history of the forces.
Exactly. You don't need a massive memory buffer to hold the history of the calculation. You just take a snapshot of the final equilibrium state, calculate the gradient, and update the model. It allows the phone to continually learn and update its weights using a tiny constant O of 1 memory footprint.
That is a staggering mathematical trick. Okay, let's step back and look at the whole picture we've painted today. By stacking these highly specific innovations, we have systematically eliminated the need for the data center.
You really have.
We start with Gemma 4, routing its 3.8 billion active parameters to save power. We feed it a multidisciplinary synthetic prime so it learns abstract math instead of rote facts. We give it the HRM so it can plan complex experiments silently without token bloat.
All on the phone.
Right. And then GraphMERT acts as the rigid map to keep the physics grounded and hallucination-free. The MD Agent 2 framework and the Darwin-Gödel machine let it autonomously trace, rewrite, and evolve its own code in a local sandbox. And finally, attention residuals and the implicit function theorem let it update its own brain on the fly using barely any memory.
When you lay the components out sequentially like that, you really see the magnitude of the shift. This isn't just an incremental improvement in hardware efficiency. It is a fundamental restructuring of how and where scientific discovery happens.
Right. Because previously, if you were a researcher trying to discover, say, a highly efficient solid-state battery material, you needed an institutional grant. You needed to wait in line for server time.
You needed $1 billion cloud computing budget. But with this architecture, the barrier to entry has literally been miniaturized. You no longer need an institutional supercomputer.
The capability to run autonomous industrial-grade physics simulations now fits in the palm of your hand. It means anyone, anywhere, can participate in the discovery of next-generation materials.
It is the ultimate democratization of science.
It really is.
Yeah.
And I want to leave you, the listener, with a final thought to mull over as we wrap up. We just spent this time walking through how a single, isolated smartphone can autonomously evolve its own physics simulations in a local sandbox.
Right.
But what happens when millions of these sovereign edge devices, all sitting in people's pockets around the world, begin securely sharing their independently evolved synthetic prime insights with each other in a decentralized global network?
That's the real question.
Exactly. If one phone acting alone is a digital scientist, well, could a globally connected swarm of smartphones eventually out-innovate the world's largest supercomputer?